Good morning, everyone. Welcome to another webinar that Editage has been bringing to you over the past few weeks. This is now the fifth webinar in a series of six webinars that Editage is bringing. And very shortly, I will introduce to you the speaker for today. My name is Daniel, and I represent Editage. And I just want to welcome all of you to this webinar. I hope you've been around for the previous ones. If you haven't, but you're interested in receiving the content of those webinars, then do let us know. We can arrange for that as well. Today's webinar topic is on the essentials of statistics for researchers, and we're very happy to have Dr. Jacob Wickham here with us to take us through this topic. I mentioned that there are six webinars in this series. This is the fifth one, and the next one is on the 16th of March, and that's on research tools for collecting, writing, publishing, and disseminating your research. And we will have Dr. Nada Ali Ibrahim to take us through that topic. Very happy to be bringing these webinars to you with our partners. Our knowledge partner is DP, the Indonesian Science Fund, and our university partner is Erlangga University. Very shortly, we'll have Dr. Ferry from Erlangga University to just encourage us with a few words. But before that, I thought let me just introduce the speaker for today, Dr. Jacob. He's senior managing editor at the journal Interactive Zoology. He's currently a senior researcher at an institute at the Russian Academy of Sciences, but comes with many years of experience as a professor at Rutgers University, previously at the Chinese Academy of Sciences, now, of course, at the Russian Academy of Sciences. He's prolifically, written and published in high impact factor journals, and brings all of that to bear. His experience as a journal editor, but also as a researcher, published author, and faculty member in training up researchers on both sides, both from the research point of view as well as from the publishing point of view. And so we're very happy to have him with us. He's been with Editage for some time now, and it's always fun when we have him for our sessions. Before he comes on, we have Dr. Ferry from Erlangga University. Dr. Ferry is faculty at Erlangga University at the Department of Community Health. He's also secretary at the Institute of Innovation, Journal Development, Publications, Intellectual Property Rights. His research interests lie in health policy, community health, maternal and child health, and he's also involved in projects with the Ministry of Health in Indonesia. So I invite Dr. Ferry to just open this session up for us, and then thereafter we'll have Dr. Jacob come to us. Dr. Ferry, please.
Yeah, thank you very much, Mr. Daniel. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Distinguished speaker, Dr. Jacob, participants, ladies and gentlemen, my dear friends of social science, health technology, and innovation at Universitas Erlangga and all over Indonesia. I'm pleased to welcome you to the webinar on the essential of statistics for researchers. This is part of a series collaboration between Editage and Universitas Erlangga. And I must mention that Editage has been our strategic partners in meeting all research need to help publish. And as we understand that statistical is a critical tool for researchers in various fields, such as medicine, my field also nursing. We need statistics, psychology, sociology, and among others. It enables researchers to analyze data, identify pattern and relationship, and draw meaningful conclusion from their research. In today's webinar, I believe our excellent speakers will cover the basic of statistics and provide us with the essential knowledge that will help us navigate the world of research. And I do believe we also can learn some common pitfalls, yeah, and errors that researchers make when interpreting statistical result. And we also believe that although you are a seasoned researcher or just starting out on the research field, yeah, this webinar will provide us with valuable insight and skill that we can apply to our daily life in academia. So by the end of the webinar, we hope that we can have a better understanding of the role of statistic in research and how it can help you make more informed decision. So without further ado, let us dive into the world of statistic and start exploring its essential. And once again, thank you so much to Editates and also Dr. Jacob, yeah, for this excellent platform and also webinar. And we hope you find this webinar informative and engaging. Yeah, thank you so much.
All right,
Thank
thank
you
you
so
very
much,
much.
Dr. Perry. Sorry, Jacob. I was just bringing you in. Please go ahead, Dr. Jacob.
Okay, so I'll share my screen. Let's get started with this webinar. And feel free to use the chat during the webinar. I always like to see the chat active over there. There we go. Share my screen. Oops. All right, can everybody see my screen? Just before we get started, I just want to confirm everybody can see my screen. Okay, the title of this webinar is Essentials of Statistics for Researchers. Again, Daniel, thank you for the introduction, and also Dr. Ferry Effendi at Erlangen University. Today I'll be talking about statistics, both from the viewpoint of a researcher and also from the viewpoint of a journal editor. My main position is a researcher, but I'm also an editor of Integrative Zoology. For the last 9 years, I've been with this journal. It's based in Beijing, China, and it's a multidisciplinary journal. And statistics is one of those key elements of every paper. When we get a new submission to the journal, we look at the experimental design. We look at the paper to see if the statistics are done correctly, if the the researchers have explored their data thoroughly, that they're using the right models. Often I get comments from reviewers on statistics, and in this regard, I see reviewers are often very, very helpful with the authors that submit their papers. They'll even offer um, you know, statistical models and even some of the code for some of the statistical programs that they're using, and will improve the paper. So usually I do get a comment or two on the statistics of every article that's submitted to the journal. So here's a brief snapshot of Editage. They're now offering statistical support, as you saw from Daniel's slides. They've helped over 500,000 researchers publish over 2 million papers. So they have a lot of experience, and now that they're continuing to serve authors, and they're trying to bridge the gap between authors and peer-reviewed publications, the journals. And I think the statistics offering is great. So this is a nice expansion of their services. And here's a little bit about me. I've been all over the place in China for most of my career. I was there from 2010 until 2021 at the Institute of Chemistry and then the Institute of Zoology. And here's a couple covers from the journal where I edit. We actually get a lot of submissions from Indonesia. We're not a Chinese journal. We're actually an international journal, and it's the flagship journal of the International Society of Zoological Sciences, which is based in Beijing. And I'm currently at the Severtsov Institute of Ecology and Evolution, Russian Academy of Sciences. I'm also an adjunct professor at Rutgers University in the U.S. So here's an outline of today's talk on statistics. whether you're a beginning researcher or a seasoned researcher, it's important to have a good grasp of statistics. And today we'll give you a broad overview of it. And it's important to understand and describe data distributions and the statistical procedures that you have available to you. Um, yeah, I'll make a brief note about how there is a trend to avoid overemphasizing p-values. Actually, I'll share with you some actually more statistics actually on journals about the reliability of p-values. So just because you don't have a significant p-value doesn't mean that the results are not biologically significant. So I'll go into into this topic a little bit, and then uh, every research paper should be able to frame a research question, and then you should have a treatment and a control where you can do statistical analyses, so you can make meaningful comparisons in your data. And then finally, I'll touch on research accuracy and precision. Here's a couple covers of the journal Integrative Zoology that I wanted to share with you. And again, you we have a not only are we an international journal, but we do receive a lot of papers from Indonesia, from Indonesian authors, and I've noticed a trend in the last like 5 years. We've had a very large increase in submissions from Indonesia, so this is great. So here's an outline of the talk. Um, I already commented on how important it is to understand the types of data you have and be able to understand and describe data distributions. I'll cover statistical procedures, in particular, parametric versus non-parametric statistics, avoiding overemphasizing p-values, how to frame a research question and do an appropriate statistical analysis, and then I'll comment on research accuracy and precision. So first of all, what are statistics? Basically, statistics are a quantitative understanding of a certain phenomenon, like a dependent variable that you'll be measuring. You'll obtain these data from surveys, and whether you include the data, if you're like a medical researcher, there's a lot of selection criteria that you can have in order to count certain data. Biologists will go and take samples, often in the field, and there's different methods for understanding the data. And one is to be able to compare treatment with the control and make meaningful comparisons, and to better understand the data. Usually, authors will, or the researchers will analyze their data, or they besides doing basic descriptive statistics, it's useful to present your data visually, and you'll use figures if the overall trends of the data are more important than the actual data points. But if the actual data points are more important than the trends, then usually these data are presented as tables in your manuscripts. But the overall goal is to gain an objective understanding of the data. And probably the most important part of your data is looking at its variability. So if you do have some figures depicting the means, or if you have a bar graph with the means, researchers, the journal editors, one of the first things they'll look at is error bars, the confidence intervals. So how spread is the data? If the data contains a very large variance, then you'll need to have a bigger sample size to be able to understand the variance. And however, if the variance is very small, researchers do not need as big a sample size. And there's actually some statistical procedures like power tests that and effect size And you, know, you can do a smaller pilot study and get an understanding of what the variance of your data is, and then you can actually predict, what sample size that you need to be able to tell uh, the difference between the means of two populations. So you'll be able to actually get an estimate of how big your sample sizes need to be from a power test. So two main functions of statistical analyses. One is to make inference about a whole population. So you'll be making some conclusions, some estimates or inferences of a entire population from a partial data set. And the partial data set is your sample. Another function of statistical analysis is to reveal the underlying structure of your data. This can be through statistical analysis, and as a result of your statistical analysis, whether you're using parametric statistics that are based on data with a normal distribution, and that are you're assuming that the two data sets have equal variances, um, and follow a normal distribution. And you'll be using parametric statistics. But if these assumptions about a normal distribution are not met, then you'll be using non-parametric statistics, or you might be doing like a data transformation before you do an analysis to make your data have a more normal distribution. So you'll be quantitatively summarizing and classifying the data obtained from a sample through your statistical analysis. And just a basic understanding of your types of data is useful. And there's lots of different types of data. One is the nominal scale. I like to call this categorical data. Here, the researchers are artificially making categories. So, here, for example, male equals 1, female equals 2. Here, the size of the values have no meaning at all. Basically, I call these dummy variables. And these are just codes that you're using to classify your data. So here, calculating averages and totals is totally meaningless. But the categories are what's important, and there's different ways to compare the data from these two categories. But these dummy variables have no meaning. Another scale is the ordinal scale. Uh, these are data that show the relative rank of what is being measured. A great example of ordinal data are journal rankings. Journals will rank themselves in relation to each other, and usually the data are displayed as a quartile range or a box and whisker plot, just to show the relative position how the ranking is, the relative rank of a certain journal or whatever you're trying to measure. Again, here calculating averages or standard deviations is meaningless. The more meaningful data is the median value or the middle value, and there's also a quartile deviation. So, basically, Q1, Q2, Q3, Q4. That's how they divide the journals, and the data is displayed as the median value, and then the 4 quarters. Another scale is the interval scale. This measures data where the differences between the objects of measurement are meaningful and equal, like temperature is one example, and IQ is another. There's no absolute zero there, but here it's possible to calculate averages and totals as well. And then the ratio scale. This is numerical data that has meaningful 0 points. For example, length, weight, blood pressure, grip strength. They have a meaningful 0 point. Temperature can also have a meaningful 0 point if you're looking at Kelvin. That's just absolute zero. But ratio scale is useful for a lot of different measurements. And here it's possible to calculate averages and totals. So basically, there's no need to clearly distinguish between interval and ratio scales. The differences between the objects of measurement. These are all meaningful data, but in reality, the data are usually separated into either qualitative data. This is the nominal scale or ordinal scales. Again, that's the categorical data. It can be like plus or minus. It's qualitative data. And the other type of data is quantitative or continuous data. And this includes interval and ratio scales. And both types of data are okay. They both have different statistical analyses. For example, qualitative data, if you look at relative ranks, the Wilcoxon rank sum test is a great non-parametric statistical test for looking at differences in the ranks. Whereas more of the classical, like ANOVA and t-tests, will test quantitative data. So to understand and describe data distributions, one thing you can do early on is explore your data and look at the distribution of your data. Before you do your statistical analyses, it's useful to construct frequency distribution tables, and you can divide your data into different levels, and you can show the frequency for each level. And this will help you understand like the spread of your data and also the distribution of your data. Is it normally distributed or not normally distributed? Of course, there's tests that you can do, and I'll tell you which tests that you can use. So a table can separate given variables into levels and records the number of data points at each level. So here is a frequency distribution table that you can. These are some testing scores, and there's ranges, and then the frequency in each range. And then you can have these other statistics like the ratio distribution and the cumulative ratio. This is additive when it sums up your data points, 50 to 60, and then it adds also the next level together and the next level after that until you have like 100% added up. So here's a histogram. This is based on this frequency table that was constructed, and you can just plot these data. And this shows the distribution of quantitative data, and it makes it better. It makes it easier to understand the data distributions visually. And you can, but I have to caution you that they can give very different impressions according to what interval that you choose. 10 points, the intervals of 10 is kind of a big range. But for the purposes of grading, that's like A, B, C, D, E for the grades, and a lot of scores, testing scores will tend to follow a normal distribution. You have this bell curve. So here it has the frequency and also the cumulative ratio. But if you change the intervals, the data can look a lot different. I think maybe the interval of 20 is a little too big of a range. I don't think that's a very useful depiction. And then the researchers went as far as showing intervals of 2, and you can actually see the entire distribution and where the scores fall. So I think either the interval of 2 or 10, they both work at giving you a good idea of the spread of the data. And here's some common histogram shapes. There's the normal distribution, then there's the bimodal distribution, and and this is where there's 2 peaks in your data. There's a distribution with an outlier, and And actually, the outlier can have a big effect on your data. And sometimes it's better to show the median score rather than the mean score if you have the outliers in your data. And here's a skewed distribution. It can either be skewed to the left or to the right. This data distribution is skewed to the left. I mentioned the journal rankings. This is qualitative data that shows the relative ranks of the journals against other journals. So here's if you look on your lower right part of your screen, this is a box and whisker plot where the line is the median, the middle value, and then the bottom box is Q3. The third quartile, the top of this box is the Q2, the top the second quartile, and then the first quartile has a huge range, actually. This is the top 25% of all the journals, the impact factor scores of all the journals in the top 25%. And then you have the bottom range, which is the bottom whisker, the Q4 bottom quartile. So that's what these data look like. Again, the median is better than the mean when you're comparing the journal rankings. And here is another way that shows the percentile on the right, and then the journal impact factor on the left, and across the years. So it's different ways to look at your data. So to obtain the median, if you have an odd number of data points, it is the value of the middle value point. So the value, the fourth rank, if there's 7 data points. And here the median is 92. And actually, this is much more useful in describing this data set because you have an outlier for your first data point. And then if you have an even number of data points, your median is the average between the 2 middle data points. And here the median is normally used in the case of outliers or non-normal distributions. If you look at this low score here, this is an outlier, and it really affects the average. The average is like less than 80. But that's not a very useful description of this data set. Here, the median, I think, is better description of the middle value. Scatter plot is another useful way to visualize your data when you're exploring your data before you do formal statistical tests. And this is an easy way to understand data distributions and correlations. So this is used frequently. Often you can add a trend line, or you can do a linear regression analysis, and you get an R-square value. And you can also do a correlation tests on these data as well. And you can get a p-value that if it's below 0.05, it means that the data are correlated. And then R-square value, just shows a relationship, the strength of the relationship of your data. So after you look at the distribution of your data and you can visualize your data, then you can start testing your data. And one of the first checks that you can do is you can check for normality and homoscedasticity. Homoscedasticity is the variances are equal between 2 populations. If you look on the lower left, these are 2 populations that the means are different, but the variances are equal. Here you can do t-tests or ANOVA. And then there's 2 populations that have unequal variances, and these will actually I'll explain how to test the variances, the assumption of equality of variances. So for the test of normality, there is a test called the Shapiro-Wilk test that you can do. And here the hypothesis is a normal, the distributions are normal. So if you get a significant Shapiro-Wilk test, and then it rejects that hypothesis that the data are normal, and then you should do a non-parametric statistics test. For a test of homoscedasticity, the assumption of equal variances, the test I like to use the most is the Levine's test. So here the null hypothesis is the variances are equal. So if you get a significant p-value of 0.05 or less, then you can reject the null hypothesis that the variances are equal. So the variances are therefore unequal, and then you can switch to a non-parametric statistical test to examine the means of your data, or the variances of your data. Basically, homoscedasticity is the distribution of two data sets are equal. They're assumed to come from the same population. So these are quick and easy tests that you can do of your data before you start doing your ANOVAs, your parametric tests, or your non-parametric tests. So again, you want to establish a hypothesis. Usually this is done before you even start collecting data. You should have a treatment group and a control group. And your null hypothesis is used to judge whether a given hypothesis is correct or not. In most cases, null hypothesis assumes that a given hypothesis is negated. So your null hypothesis will be, there is no difference between population 1 and population 2. That is usually what a null hypothesis is. And then you have an alternative hypothesis, is that it's the opposing hypothesis to the null hypothesis. And if you accept the alternative hypothesis, you say there is a difference between these two groups that you're comparing. So in the end, if it's whether it's a medical paper or a biology paper, your null hypothesis is the new method has no effect, and the alternative hypothesis is the new method does have an effect. And this is a research question in medicine down here. A new method of muscle training is discovered. Is it more effective than other methods? So null hypothesis has no effect, and alternative hypothesis, it has an effect. This procedure is important. I talked about p-values already. The p-values are tested at a certain significance level, and your significance level is this alpha. And alpha is your confidence level. And this is usually set at 0.05. And this is a great compromise between type 1 and type 2 error in hypothesis testing. And usually your alpha level is set before conducting any statistics. I think 0.05 is a conservative value. You basically have a 1 in 20 chance that the differences that you're observing in your data collection, the differences between the two populations, you have a 1 in 20 chance that the differences that you're observing are due to random chance alone. And this is generally accepted across biology. If you're an engineer, you'd probably be using much smaller alpha levels, because if you're building a bridge, you want to have much less potential for error, or having the differences due to random chance to actually be very small. There's one and two-tailed tests. If you have a good idea if one population is bigger than the other one, you can do a one-tailed test. This is basically, if you're looking at the bell curve of the data distribution, you can actually test the differences between two populations on just one side of this bell curve. So if you know in advance, if one population is bigger than the other population with their values, you can do a one-tailed test. But if you cannot predict the results between two populations, this this confidence interval region is set on both sides of the reference point. This is a two-tailed test. And commonly when you're using t-tests, you can do one-tailed or two-tailed t-test. And the two-tailed t-test, you have the differences are 0.025% chance of being wrong on each side. And that's where you come up with that p-value of 0.05 from the confidence interval of 0.05. I discussed the p-values. Basically, a statistical test will give you a probability value, this p-value. And then this is the probability that a particular statistic occurs under the null hypothesis. The p-value, if it's below a significance level of, say, 0.05, then the null hypothesis is rejected and the alternative hypothesis is accepted. If the p-value is greater than this 0.05 significance level, then the null hypothesis will say failed to reject. You can accept the null hypothesis. There is no difference. And again, in natural sciences, this is usually set at 0.05 or 0.01. I just wanted to briefly talk about statistical error. Type 1 error, this is that you're rejecting the null hypothesis. However, there really is no difference. So you're deeming the results significant when in fact they are not. And then type 2 error is when you reject the alternative hypothesis even when it is true. So basically in type 2 error, your results are deemed not significant. Oh, there is no difference, but actually there is a difference. Maybe your sample size is not big enough to detect the differences. So those are the differences between type 1 and type 2 errors. And actually, setting the alpha value, the confidence value at 0.05 is a good compromise between type 1 and type 2 errors. So what is the opposite of a significant difference? So you can say there is a difference, and then the opposite is we cannot say that there is a difference. There might actually be a statistical difference between these two populations, but your sample size may not be big enough to actually detect it. So all you can say in hypothesis testing is that we can't say that there is a difference. We didn't detect it using our statistical analysis. So, and why can you say, why do you have to say we cannot say there is a difference? Well, you can't accept the null hypothesis. So now I want to talk about avoiding overemphasizing of p-values. This is actually an interesting question. A lot of journals have looked into the p-values. And here is a study that was done. They analyzed almost 800 papers across 5 journals. And they found that about half of the papers mistakenly assumed a non-significant means of they have no effect when in fact they were significant. So they looked at the p-values, and over half the articles had wrongly interpreted statistical significance. So be careful. Don't interpret the findings on your paper based on the significance or non-significance alone. You will want to look at other aspects of your data. So with the p-value of 0.05 and the significance level at 0.05, here are 100 studies, and each study is one sample. And if you look at the yellow discs here, these are, you have significant results statistically, but they only occurred by random chance. So this is the probability that the differences that you're observing between the two populations occurred by random chance alone. And then in the red, here's the result did not occur by chance. So you actually have a real significant difference. So these 5 studies, this is why the p-value is 0.05. 5% of the time, you're going to be wrong. And this is an acceptable level of being wrong. So these are, the differences are by just chance alone. So if you have one of these yellow disk studies, yellow circle, basically, if you have one of those studies, you conclude that there's a significant difference, even when there is not one. And this is type 1 error. This is a classic example of type 1 error. So if alpha is 0.05 or 5%, this will occur 5 out of 100 times. And this is accepted across the biological sciences as a matter of custom. So if the p-value is less than 0.05, results are deemed statistically significant, not the product of chance. But in addition to p-values, you need to look at other things like what is the variation, what is the variance, how spread are your data, what is the strength of the relationship. If you look at a scatter plot and you're looking at a regression, so you can look at other parameters of your data to help you draw your conclusions. One example is correlation coefficient. If you have a scatter plot, you can calculate your R, and the correlation coefficient is R, and this shows a very strong correlation. This is just an example. And the probability of the strong correlation is, the probability that there is no correlation is less than 5%. So you can, with confidence, state that there is a significant correlation between your data point. So the p-values here, these are strongly influenced by the number of data points, whereas correlations can be interpreted using the correlation coefficient. So you have to be careful. Sometimes correlation does not imply causation. If the p-value, even if it's very, very small, you cannot you cannot say it is meaningful in terms of the strength of the correlation. You have to interpret the correlation as well. So if the R is high, I've seen some significant p-values when R is very, very low. So you have to be actually careful when you're interpreting the data. So look at more than just p-values. Effect size is another parameter of your data that you can discuss in a paper. This is the ratio of change in distribution, and this is calculated looking at the differences between the means over the standard deviation pooled. So a large effect size, there's your elephant, that's 0.08 or 0.8. Moderate is described by the duck here at 0.5, or you can have a very small effect size, which is 0.2 to 0.3. And this shows what is the strength of the difference between the two means of your population. And you can use this. A useful analogy to understand effect size is to look at noise in your signal. So changes will become more difficult to detect if you have a greater background noise. So hopefully, if you have a large effect size, you can actually distinguish the differences from the background noise. So here are your 3 different effect sizes, and these trees are the noise. So if you have a small effect size or even a medium-sized one, it'll be hard to distinguish the differences. But maybe the large effect size, that elephant there, you'll be able to distinguish the difference between 2 means. So again, changes become more difficult to detect with larger background noise. So hopefully your effect size is large. And here's a good depiction of the signal to noise ratio. So hopefully the effect sizes are big and you can distinguish your signal from the background noise. Another concept I wanted to cover is the 95% confidence interval. This is the effect of the variation. This will actually decrease as your sample size increases. So if you have a very large variance, you will want to have a large sample size, because then the effect of that variance will be diminished with increased sample size. And this is related to hypothesis testing and parameter estimation. So one thing you can do is a power test, and this will tell you how big of a sample size you need to be able to analyze your data and take into account how large your variance is. And basically, this 1.95, this is the standard deviations. And if you look at this bell curve, here at 95.45% confidence intervals falls within 2 standard deviations. So here you have a 95% chance your data will fall in this part of the curve. And this is your 95% confidence interval. So if you go slightly below 2 standard deviations, you get that 95%. So it's 1.96 standard deviations. And this helps to detect the differences that you have between 2 populations. So getting into research questions and statistical analyses, I wanted to differentiate between parameter estimation and hypothesis testing. So is there a difference? If you're asking this question, if there's a difference between 2 groups, the emphasis here is on the 95% confidence intervals and the effect sizes. Is there a difference? Or if you're asking a question, does a difference occur or not? This has emphasis on the statistical significance using p-values. So is there a statistical difference, really? Does it occur or not? Those look at p-values. So here are statistical procedures relevant to parameter testing. Again, the 95% confidence interval is important. Effect size. In medicine, there's minimally clinically important differences, and then minimally detectable changes. These are important aspects of some medical data. You can also do a statistical power calculation and a sample size calculation to be able to predict how big is your sample size that you need, and to take into account the variance of your data. So here's a research question format called PCOT or PAYCOT. You have a population, then you have an intervention or exposure, what is done to the population, then a comparison, and then you have an outcome, some measurable, something that's measured by the scientist or the medical professional, and then you have a duration of the experiment. And this is easily understood for studies involving interventions like medical treatment, but this is not applicable in observational studies. So here is a PCOT for non-intervention studies. So here's an approach to exposure. How can we compare or stratify the outcomes? Here you're looking at the presence of dementia, affect walking ability 1 year after stroke. So here the question is, what is the relationship between cognitive functioning and walking ability 1 year after the stroke? So here there's no intervention. They're just looking at whether the individual had a stroke or not. There's no medical treatments here. And this is non-exposure, non-intervention studies. So here the sampling interval is 1 year, and the measurements are taken at the time of the stroke and then 1 year later. So requirements of a good study objective: you should have all these parts of the study. You should have a population that's easily identifiable, the exposure or intervention, and then you compare the 2 groups, and then you have an outcome, and then the time. In this question, this study aims to provide a summary estimate of the extent to which cannabis use in adolescence is associated with the risk of developing subsequent major depression, anxiety, and suicidal behavior. So here, the population is the adolescent population. The intervention or exposure is cannabis use. The comparison, this is not a good study because it's hard to tell what their control group is, but then the observation is depression, anxiety, or suicidal behavior. So here they didn't have a control group, and it doesn't really show the time interval. So this is not a good study objective. And here is where the research question is very clear and the study aim is clear. Here, the elderly people with memory lapses, here they do exercise as an intervention, and then they do tablet-based memory training, and then they observe the memory function. And here you have a discrete time period, 8 weeks or 1 year. So here you can immediately determine the aim of the study. You can also look at the groups that are being compared. So here the aim is to evaluate the preventative effects of 12 months follow-up of an exercise program on memory loss among elderly people diagnosed with MCI. This is mild cognitive impairment after seeking treatment for forgetfulness compared to memory training alone. So these are you have a population that's seeking treatment and then a population that doesn't have treatment. So here you can compare two groups. And if you have a well-written study objective like this, then it suggests that statistical tests and the results and tables and figures will be used. And here you have a control and then the intervention, and you can actually compare the differences between the control and the intervention. So finally, I'd like to get into accuracy and precision. These are important aspects of any research design. How can we pose a significant research question? You should be able to determine how much error is in your sample, and then you can minimize the errors and have the highest degree of precision as possible. So bias versus precision. So accuracy is how are we largely accurate no matter how many times we sample. And then are you getting close to the target? And precision is, do the darts land in the same place no matter how many times we throw it? And that's your distribution of your data. So this is high accuracy with low bias when you're hitting the target. And this is if you have multiple measurements and all the measurements are very close to each other. These are very highly precise data. This is high accuracy but low precision. So if you have an average, the average is actually the bullseye, but the precision is low. So here you have a large variance, but you have a meaningful average, and the accuracy is high on average. And this is low accuracy but high precision. This could happen if you don't calibrate an instrument. You're taking very, very precise measurements, but your instrument is not calibrated. So it's not accurate at all, but it is very precise. And these are just the 4 different combinations. You can have low accuracy and precision, which is the worst of the scenarios. And then you can have high accuracy and precision with all the darts hitting the target. So again, upper left, again, you have high accuracy, but the high variance. But on the lower right, you have very low accuracy, but high precision. So if you look at different studies in the quality of the evidence, you can have less bias in randomized controlled trials or meta-analyses, like a sample of randomized controlled trials. And then you have a high bias, more error, and then the quality of evidence is lower. If you don't have a good study design, if you have quasi experiments or just non-experimental descriptive studies, and that are not randomized controlled trials. So you can look at the overall quality of your evidence. So to deal with bias, you should have a randomization of your samples. You should have strict criteria for non-inclusion in studies. You may measure some factors that create bias, and you want to analyze factors that may create bias via subgroups. So here's an outcome. There's 3 different exposures. When you're establishing your research question, it's important to anticipate which statistical tests will be used, parametric statistics or non-parametric. When I gave you, the Levine's test and the Shapiro-Wilks test to test for the normality and then homoscedasticity, the equal variances in your populations. So basically, you can try to reduce the potential effects of the bias by using random sampling, and then the probability of each sample point. You want to have independent data where the chance of inclusion in the experiment is equal for all data points, and that leads to less biased statistics. So I was just going to conclude here. There's some tools for statistics because we're running short on time. Yeah. When you're displaying your statistics in your research papers, very quickly, there's you can use images, or you can use what we call vector images. Vector images, just really quickly, is vector and raster. Raster are images. Vector, you can mathematically describe the data points. I'll just show you the image on the left here is a graph in vector form, where each of these data points has a mathematical description of it. You can edit each data point. It's resolution independent. Whereas on the right, this is like a Photoshop image. Here you cannot edit the data points, and it's resolution dependent. So when you're graphing your statistics, try to graph it in vector form so you can have a mathematical description of all your data points. And that's my take-home message there. And there's different tools that you can use for vector graphics. Some of your statistical programs will help you with this. So you can do vector graphics in MS Excel or Google Charts. There's also RStudio. So it depends on the statistical program that you're using. So here are some graphical or statistical programs that can be used depending on which ones you're comfortable with. We can also help you out at Editage with a proper statistical analysis. I've seen a lot of papers just as a journal editor. This is like an open sourced statistical program called R, and I encourage everyone to learn R. This has basically become mainstream over the past 10 years. If you want to start as a very beginner, there's a link here. There's a wonderful reference book here, and it can give you some sample data sets, and you can practice plotting your statistics. And this is a wonderful reference for beginners. So here's some take-home messages as we're wrapping up this webinar. It's important to choose the right statistical tools or your tests, your proper statistical test according to the type and distribution of your data. I encourage you to explore your data. Your data exploration should help you, just plotting the frequency distributions. You can check your raw data, understand it, and you can check its distribution visually. And this will help you, choose which statistical test that you will use. So you want to estimate the parameters in your study, have meaningful parameters, have your p-values tested. If you're doing statistical tests to check the differences between two populations, it's important to have a very clear research question with controls and treatments. Make sure your statistical test that you've chosen actually follows logically from your statement of your research objective, and take appropriate measures to increase your study's accuracy and precision, like randomizing the samples, and each data point is independent. And finally, learn R. It's free. Again, here's the previous slide. You can download this link. We'll share this link with you after the presentation. And at this point, I'll be happy to take any questions you may have. And thank you for your attention. I'll stop sharing. So I'd like to open up for a Q&A. If you've typed in some questions on the right side of your screen, I'll be very happy to answer them. Uh, Again, there's a feedback form. You can click on this feedback form because we'll be doing more webinars in the future, either at your university or at the national level, like this webinar. So just to get to a couple of questions. Here's a question from Ika. Here's the thing with quantitative data, as a questionnaire as an instrument. The majority of people scale them, which make them troublesome when analyzing with t-tests and parametric tests, but they did it anyways. Actually, that they chose the wrong test for like questionnaire data. Should be qualitative. Um, yeah, yeah, with qualitative tests, they should be using non-parametric statistics. So these are inappropriate tests. Actually, that's not very surprising that was done. If you looked at that study in Nature, out of almost 800 manuscripts, over half of them either used the wrong tests or they were wrongly interpreted. So that's another example of that. Those were nominal data points. So I think the reviewers and the editors should have caught that. Um, yeah, yeah. A lot of journals actually they do publish survey data, so you have to make sure that the appropriate tests were done. So I also disagree with that, Likert. So which means I agree with the ICA. Another question that was flagged here. How about the importance of non-parametric statistical analyses? Actually, I have no problem with non-parametrics. Actually, it's the assumptions of normal distribution and assumptions of equality of variances, homoscedasticity. In the real world, when you're studying a population and you have a limited sample size, often the data are very messy. They need to be transformed before you do a statistical test. There's a lot of, I wouldn't say wrongful manipulation, but there's appropriate manipulations of your data based on distribution, normal distribution, non-normal distribution, and equality of the variances. I see this all the time where the data are not normal and the researchers will switch to non-parametric statistics tests. Instead of a classic ANOVA, I've seen Kruskal-Wallis ANOVAs used to compare the differences between groups. And there's no problem with using non-parametric statistics. They're more flexible for qualitative versus quantitative data and for non-normal data. It's perfectly okay to use non-parametric statistics. And Ika has one more question. Suppose we are doing a t-test. Which of these p-value or t-test determine the significance? T-tests, you're comparing, it's one of your basic tests that you learn to compare differences between means. I would just caution researchers to avoid doing too many t-tests because that'll lower the power of your test. It's better to do ANOVA compared to doing multiple t-tests. And if you must do multiple t-tests, you can do a Bonferroni correction. And basically, you're dividing the p-value of 0.05 divided by the number of t-tests that you have. And you can use Bonferroni corrected p-values and still make reliable inferences on your data. So it's okay to do the t-test if you're comparing two groups, but if you're comparing 3, 4, or 5 groups, it's better to switch to ANOVA. You can also look if you're doing a one-tailed versus a two-tailed test. The two-tailed tests, you have a p of 0.025, so it's half of 0.05 on each tail. But if you have a good idea, if one population is bigger than the other, then you can do a test of alpha at 0.05 on just one of the tails. And I think we have time for one more question. I get to the last one here. Can you please tell me about the tools that give more precise results regarding statistical analyses when writing a review paper? So, um, actually, review papers, um, you know, you may have a metadata, like an analysis of lots of papers. And actually, you can use a parametric statistics if you're doing a meta-analysis of multiple randomized controlled trials, which you may have in a review paper. Actually, review papers you know, can can give new perspectives on data. Because it's actually a sample of samples, and they tend to have less bias, and they actually can give you novel inferences of a particular treatment or study. As far as more precise results, if you are doing ANOVA tests, you can pick different post hoc comparisons. For example, I think Bonferroni is a very strict test. The differences in the means actually have to be very, very large and detectable, and but there's more conservative tests like the least square differences, so LSD tests. Here these are post hoc comparisons that the differences between the groups might not be it's not as a rigorous a test compared to the Bonferroni test. So just be careful on which post hoc comparisons that you choose. Don't choose a very conservative one. Choose a more rigorous one, and that has more reliably. You can detect the differences between two populations. So with that, I think we're done. We answered all the questions. Daniel, if you want to wrap up, I will give the floor to you. So thank you,
Thank
everyone.
you. Yeah, thank you, Dr. Jacob. Thank you all of us for for attending, for participating, for the questions, and I do hope you filled in the feedback form. We'd love to hear your views. There is a webinar coming up next week as well, so be sure to mark your calendar for that. We've put in the link in the chat window, so you can complete your registration for that. We have the statistical services. Training is one aspect of it, but we also provide services and everything from planning your study to designing a questionnaire to inferential statistical analysis to even post submission support. If you have received questions from a journal or your peer reviewers on the statistics that have been done, and you need support in terms of how to respond, so then that's something that we'd be happy to support you with as well. Just want to say that there's a currently all of these services. You don't have to. I mean, you can go to our website and access them. Uh, but something that we've been running recently is where you can book a free consult with our in-house statistician. So if this is something you'd like to do, you have a question on statistics, you're not entirely sure what kind of support you need, or you just need to discuss the challenges you're facing with respect to analysis or a study you're doing, then feel free. This is currently as the campaign we're running it, where you can book a free consult. Just go to our website. The link's been put up here, and you can book a slot and speak with our in-house statistician, and they'll be able to just guide you through what you need to do, and if at all you need support with services. So that's something I'd encourage all of you to explore, and yeah, feel free to write into us with your feedback, with any support you need, and if you'd like your university to work with editage in a larger way, then all of that is something that you can write in to us with. Right. So keep your questions coming. The link for the recording of this session, as well as the slides and certificates of participation, will all be shared with you in a few days. So you will have all this information, and we hope to see you at the next webinar. Thank you so much.
Hey, thank you, everyone. Thanks for coming to the webinar.
Bye bye.
Bye.